Okay, let's carry on with 13.4. Basically what we've been saying is that kinetics of a particle, force and acceleration, is really based on Newton's second law, F equals ma, and we also saw that sum of the forces equals ma. This is again Newton's second law, but it's the equation of motion. So if I wake you up in the middle of the night and I say, what is the equation of motion? Right, then you should be able to say sum of the forces is equal to mass times acceleration. And what we've seen is that the resultant force, the acceleration of the particle that has mass m is in the same direction as the resultant force. So we saw that we can have multiple forces acting on a particle, and if all those forces are unbalanced, then it will cause the particle that has mass m, to accelerate. Okay? Now, the important thing to notice is that what we've seen before was just let's just call it a general equation of motion. Okay? Sum of the forces equals mass times acceleration. We didn't designate a coordinate system. So if you remember in chapter 12, kinematics, we looked at different coordinate systems. We looked at rectangular coordinate system. We looked at the normal and tangential coordinate system. And even, we didn't look at it, but I did mention it, I believe, in class. I'm not sure, but definitely in the videos. There's even a cylindrical coordinate system. So if I'm not mistaken, this was 12.5, this was 12.7, and that was 12.8, although we never did this. The point is, guys, you can have a generic statement like this, right? Sum of the forces equals mass times acceleration. But when it comes to analyzing a real problem, we need to determine what coordinate system we're going to use, right? The coordinate system defines how we will solve the problem. So we could solve the problem using rectangular coordinate system, normal and tangential, or cylindrical coordinate system, although we didn't do this, okay? So the basic idea here in chapter 13.4 is we will look at rectangular coordinates, the equations of motion, but we look at we describe this equation using rectangular coordinate system. And just to save you a lot of time, okay, in general, when we are working with kinetics and we are solving these problems, when we have rectilinear motion, straight line, okay, straight line motion, we will most likely analyze the problem using rectangular coordinates. Have you got that? If you're having a problem where the particle moves in a straight line, then most likely the way to solve it is to set up this equation using rectangular coordinate system. Okay? So let's have a look here. There is your, let me try to just zoom in a bit. Okay? So there is your equation of motion. It looks general. We don't know what coordinate system it's in. But then let us convert it into essentially the rectangular coordinate system, which is this. Okay? All we're saying is all the forces in the x, all the x forces times the unit vector I, and we carry this out, and we end up with this. Okay? These are our three equations of motion in the x, y, and z directions. Okay? So this is our rectangular coordinate system. And remember, we would generally use this when we have straight line motion. Okay? We will see later when we have curvilinear motion, we will mostly use the normal and tangential coordinate system. Okay? So just quickly, what I said. Okay, so I hope you've got this now. Let me just zoom out again. What I said before in a previous video is that the basic idea is that we have this, right? Sum of the forces equals mass times acceleration. And a lot of the problems give us the force information, and we are required to calculate the kinematic information. It's also possible to have kinematic information and then be required to calculate force information. But I'm just going to quickly, in 1 minute, show you what I mean by this. Okay? So let's have a look here. Example 13.1. I'm not going to go through it. I'm just going to show you what I mean. We have a problem here. It has some force information, right? There's mass, 50 kilograms. It has force information, okay? There is some other kinematic information. For example, there's time, and there's some more force information, okay? The point is, we start off, I'm just trying to give you a general idea of how these problems are solved. We start off with our equations of motion, right? F equals ma, F equals ma. We are given force information. We then use that to calculate some kinematic information, which then helps us calculate some more kinematic information, right? We use the force information to calculate the acceleration here. Then we took that acceleration and we were able to calculate velocity. See? Kinematic information. Again, I'm going to jump now to 13.2. We're given mass. We're given force, okay? So the idea is, I'll analyze one of these problems in detail in a minute or in the next video. But we're given force information. Do you see the equation of motion? And we get some kinematic information. We take that kinematic information to determine more kinematic information, right? Again here, force information. We use the force information in the equation of motion. We calculate some kinematic information, and we use that to determine more kinematic information, okay? So I hope that just gives you a bit of a bird's eye view of how we use force information to determine kinematic information. Cheers.